Hello, everyone. Welcome to another open seminar of the AI Evaluation Program. I'm so happy you're here. Hi, Paulina. Hi, Julie, Jael, Maxwell, Harshit. I see some familiar faces. I see some new names. Thank you for joining our community. I want to know in the chat before we begin, is this the first time you're joining the seminar, or is it you've joined before? You can, first time for Richard, lovely. Let's see. I'm gonna drop some questions here and you can just react if that's easier. And we can just do a time. Julie's an all-timer. Yeah, you're already a classic by now, Julie. Well, thank you for being here. So before we begin, so these are open lectures from the program, the AI evaluation program. I'm sorry, we keep getting requests for the note takers. All right. So this is a lecture from the A evaluation program. Right now we're on module 8. So we're seeing agentic evaluations, alignment, and control evaluations. And today we're going to have a talk by Dr. Cozmin Ududec on agentic evaluation. So these are the same lectures that our students are seeing. And what we think is, this is prime contact from like top faculty and researchers and practitioners, and we feel like it's a shame to keep it all only for 40 people. So we want to open the doors as much as possible. That's why we're having an open seminar today. We're having an open seminar tomorrow, and we will have maybe a couple more seminars to go in the next couple of weeks. So today we have Cosmin. He leads the team for developing how UK AI Security Institute evaluates frontier AI systems. He has a PhD in quantum physics from the University of Waterloo and Perimeter Institute for Theoretical Physics, where he worked on reconstructing quantum theory from first principles. And before joining AEC, he spent a decade leading applied research at the intersection of machine learning, probabilistic modeling, and complex systems. As I said, we're gonna figure out how we approach the challenge of evaluating AI agents. We know more or less how to test a model that produces an answer. We give an input, we get an output, but we don't know really how to test a system that acts. And so with agents, the picture gets a lot messier. So let me admit the rest of the people who are joining. And with that, I give it to you, Cosmin. It's all yours.
Great, thank you. Hello, everyone. I'll be talking about a whole bunch of different aspects of agent evals, like Andrina was saying, that make things really, really complicated and messy. So I'll be talking a lot about what kinds of things can go wrong, some scaffolding, inference scaling, how you can do transcript analysis for quality assurance, and a few more speculative things about what agent evals might look like in the future. Before I get into all of that, I think there's kind of a theme that'll be running throughout the lecture today, which is around the sort of sensitivity of what you observe to a whole bunch of different choices and details in your evaluation that are often, I think, too hidden. So I'll start with three numbers. So if people have seen model developers or in evaluation cards, in papers, people often talk about scores. What did this agent score on this benchmark? And there's a lot hiding behind these numbers. So, for example, the first number here, 50% of tasks in a major agent benchmark had errors. So a group at Princeton and some other orgs looked at 13 frontier models on a benchmark called TauBench, which looks at kind of customer service requests. When they looked at the actual transcripts of the agents working on these tasks, they found that half the tasks had errors. So there were bugs in how the tasks were scored or graded. There were ambiguous instructions, database errors and inconsistencies, et cetera, et cetera. And after removing all of these, the success rates, the pass rates, roughly doubled across these 13 models. The third number here, the 42% to 95%, is from a paper on another benchmark called CoreBench, which is about scientific reproducibility of papers. And Opus 4.5 scored 42% with one scaffold, so one sort of agentic structure around the model. And The same model tested with Claude Code, so a different scaffold, scored, I think, 78%, or no, sorry, 95%. So after fixing a bunch of grading errors again, it got to 95%. So the same model, the same benchmark, different scaffold, better grading goes from 42% to 95%. And so a benchmark score by itself doesn't tell you very much. There's all these hidden things that can affect it quite a lot. So it's shaped by the task, how the task is set up, the particular scaffold, the compute budget, the scoring method, etc. And each of these choices can change the result. So I'll be talking about all of these things in more detail. Hopefully you'll get a sort of stronger sense of the kind of language around these things, what to look out for, how to improve your own agent evals when you're running them. So what are agent evals to start? So last time, if people were here in module 5, we talked about different kinds of evaluations, from question answer to expert red teaming. And I think I had on one of the slides that grading is easy for agent evals, which was a little bit misleading, I think. So that again, today we'll be talking a lot about how agent evals are not easy to score or grade. And we'll do much more of a deep dive into this. So what makes a task agentic? There's 4 aspects. First is tool use. So the model can execute code, run terminal commands, navigate a browser, read and write files on a computer. So there's a sense in which it acts in an environment rather than just generating an answer to a user query. The second is that the interaction is multi-step. And the sort of standard pattern is called REACT, which stands for reasoning plus acting. So the model thinks about what it's going to do, does it, maybe it's calling a tool, it observes the result from its environment, and then it thinks again, and then it acts again, etc. And this is sort of run in a loop that can go for dozens or hundreds of turns until some condition is met. The budget runs out, or the task ends because the model has succeeded or failed in some form. And so on the right here, this diagram sort of shows this structure. So there's a user request, which may be the task prompt, which is, what is the goal of the model? What is it trying to achieve? And then the model reasons, it outputs a message, it outputs a tool call, it gets a tool response, and then it repeats. And until the task ends. The third aspect of agentic tasks is that the environments are in some sense more realistic. They're not just chat interfaces. So I put real in quotes because there's a big open question around how realistic are these environments. But typically what they look like are Docker containers, real browsers, actual terminal sessions, actual file systems on a computer. And so the model is interacting with this real software environment. And the question is, how realistic is that software environment compared to what may be an actual typical use case that someone is actually doing, or if it's more like a toy model of a real environment. And the last aspect is the stopping conditions, which I mentioned a second ago. So some agent tasks have clear endpoints. For example, in a capture the flag challenge, you've either found the flag or you haven't. In benchmarks like SweBench, the tests either pass or they don't. So the model, the agent is writing code that has to pass some tests in order to succeed. And other tasks may be much more open-ended and may not have super clear success criteria. So this is something you should look out for very specifically, is like, what are the stopping conditions? How are they defined? Are they really precise? Are they ambiguous? And a lot of benchmarks have issues with this in particular. How easy it is to determine whether the conditions have been met for the agent to succeed on the task can be a hard problem. A couple of other points of sort of terminology, some terms I'll use throughout. So by task, I mean like a single item in a benchmark, like a single test or a single unit that you're measuring, where the agent has a specific goal in mind that it has to achieve, given some success criteria. A trial or an attempt is one run through the task. So you can run the task multiple times to get better sample statistics to see how the agent behaves and how often it succeeds. And then the scaffold or harness is the full system that the model is bundled in. So for example, the React loop that I mentioned, and there's many other variants. And then transcript or log is the record of what the agent did. So all of the input and output messages, all of the tool calls, the tool call responses, etc. So there's a lot of different agent benchmarks out there, testing for very different things, different kinds of domains, different topics, different kinds of goals. So one very popular one is SweBench, and there's different versions of this, like SweBench Verified, SweBench Pro. This tests whether an agent can fix bugs from real GitHub repositories. Another is Web Arena, which is focused on web navigation. SciBench looks at cybersecurity challenges framed as these capture the flag tasks. And there's loads of others. And each measures something different. Each has its own kind of failure modes. For example, for SweBench, the unit tests might be too narrow and reject correct solutions. In TauBench, documents can conflict with each other. So these are sort of known issues with some of these benchmarks. CoreBench, some researchers found that the particular conditions for success, that sort of the model has to output a particular number that solves the task. The numerical matching can be too strict, and then the model fails even though it's really, really, really close. And there's loads of issues like this that come up. And there's a few papers that talk about this. Many of these benchmarks are used by the model developers in their system cards, so you can sort of find these being run by many organizations, including the model developers. Let's see. So before we look at scoring in more detail, I thought it'd be worthwhile discussing a bit more what makes agent tasks hard, or the kind of different dimensions of this. So first is what I call the work graph, or the complexity of the task. So you can imagine that you're trying to fix bugs in a GitHub repo, and you have you have some bit of evidence of what the problem might be. You have to make a decision of which aspect to fix first. What code do you write? What other file do you look at? Do you go and read some API documents? At every turn of the agent task, you may have this kind of branching decision process. So there are many plausible paths for what to do next, or what approaches you should take, what strategies you should use. And depending on the task, this work graph, this complexity can get very large. So there are tasks that people run agents on that it may take humans upwards of 8 hours to complete the task. So you can imagine the number of kind of decisions in such a task. The second aspect is the potential for compounding error. So because you have all of these decisions you have to make, if you make a small mistake at the beginning, this can sort of compound over the subsequent turns, over the horizon of the task. And then you can imagine that even if you have small errors at each turn, or just a few of these, if you have many, many turns, T, which can potentially be hundreds, the success rate, like how likely are you to get all of the right answer at the very end, can go to zero very quickly. The third aspect is how irrecoverable or punishing the task is. So you can imagine in some cases, if you make a mistake, you can reverse it. You can sort of notice that you've made a mistake. You've written a wrong line of code. You can go back and fix it if you have the right test. Other kinds of mistakes can waste substantial amount of time or effort or compute, or they may corrupt the state of the environment in a way that's irreversible. Like, let's say you accidentally delete a file that's crucial for you to complete your task, and there's no backup of that file, then it's very hard for you to finish. The fourth aspect is what I call self-verification quality, which is, can the agent tell if it's on the right track? So how much feedback can it get sort of locally when it's making all these decisions? Can it know if it's done something wrong? How easy is it? How expensive is it for it to check if it's done something correctly or incorrectly? And this lets the agent potentially focus its efforts better. It sort of tells it if it's on the right track or not. And so tasks where you have very weak feedback may result in the agent kind of exploring randomly or just getting lost. And as we'll see later, this potentially has an effect on whether inference scaling works, whether you give the agent more turns, does it actually improve the success rate? So for example, many software engineering tasks have strong self-verification because you can run tests, you can build tests and run them to see if your code is correct. Other tasks that are maybe less strongly specified, maybe you're not quite sure what the outcome, what a good outcome looks like. Maybe you don't have this kind of local self-verification. And the final one is the distribution of skills and the difficulty per part of the task. So you can imagine a really big task, maybe you have to do various things inside of it, and you may need different skills to complete those different subcomponents. And the question is whether one particular step maybe requires rare expertise, or whether many steps are very routine. How much depth do you need in a particular domain to be able to complete that step? Versus how much breadth do you need across many domains or many areas of expertise to complete the task. This is kind of a fuzzy sort of categorization of these things. There's different people have different ways of thinking about this, but I find this just kind of useful to sort of in the back of your mind when you see a set of tasks, like where roughly do they fit into these dimensions? Any questions at this point?
Questions? Seems like we're good so far.
Cool. Okay. I'll keep going. So at the start, I talked about these issues with scoring and how much scores can move. So now I'll talk a bit more about, like, in particular, specifically the kinds of things that affect scores. So every run of an evaluation, we can think of it as an evaluation protocol, and they all have these sort of 4 types of settings or 4 dimensions of variation. And as you change each of these, you're actually changing what you're measuring. So the first is what we might call the inference settings, which are things like reasoning effort, the temperature of the model, sampling strategy, the number of turns that you allow it, the number of the token budget, for example, like when the task ends, can have a big effect. The second is the scaffolding, in particular, what tools the model has available, how those tools are accessed, what particular agent framework the model has access to. Is it a React loop or something more complex? And how many sort of retries do you give it, things like that. Then, of course, there's the task itself. What is the prompt for the task? What instructions is the model given? What sort of format does the output have to be in? So you can imagine tasks where the instructions aren't really clear to the model, and maybe it gets lost because of that, versus you give it a really clear, detailed outline of what it's trying to achieve. Maybe it has a higher chance of meeting those requirements. And then there's scoring, which I've alluded to before, which includes things like how you're judging the final outcome. So is it based on some unit tests for the code that the agent has written? Is the output some particular answer to a question, like whether it's found the flag or not, so you just do string matching? Or is the outcome much more nebulous and harder to grade or evaluate? So maybe you need LLM as a judge or a human review to check the quality of the solution. And each of these has different failure modes, and sort of trade-offs in when they're useful and when they're not useful. So when somebody reports a score, it's really valuable to know what were all of these precise settings to help you interpret that result. And in many cases, people don't report sufficient details in the evaluation cards in papers to have a really strong understanding of what was actually done. If, for example, if you want to replicate that result, or to know whether that result is surprising or not. So, for example, if you don't know the inference budget, the reasoning effort, maybe you don't know whether 40% is high or low, whether that's a reasonable number. And it's also important to make sure that when you're comparing across models, you should have the same settings, right? You should run the same protocol. Otherwise, you're not really comparing apples to apples. Okay, so for scaffolding, as I mentioned before, there's a
Please.
question. There's a couple
Yeah,
questions. Yeah.
we have two questions actually. So something you said just light up a bulb here. Bernardo.
Oh, thank you. Thank you, Andrina, and thank you, Cosmin, for such a great lecture. When we say agentic, we, I mean, yeah, when you ask model to make a particular task, maybe that particular task might be too complex, for example, in coding. I'm thinking specifically about cloud code. It usually deploys kind of several agents
Yeah.
to perform different tasks.
Yeah.
So when we say agentic, it also applies when I have several multi-agent scenarios doing different tasks.
Yeah.
And does that also is usually evaluated? How many agents or specialized agents do you use? Or is
Yeah.
all comprising the token or the cost of that particular
Yeah.
yep.
Yeah, so yeah, that's a good question, and I think I have something on the slide exactly on that. So that I would say that's part of the harness or the scaffold. What kind of policy you allow for the agent, whether it can spin up sub agents or whether you in fact you have multiple agents working on the same task. So the kind of there's a you can think of maybe a hierarchical structure. Like you have a bare model, maybe like a chat interface. I wouldn't say that's agentic. If you give that model tool access, like web access or like the ability to run code, that's getting more into an agentic setup. Then you have explicitly agentic frameworks like React loops, where you have this structure where the model reads some context, does some reasoning, decides what to do next, calls a tool, and then repeats. Then there are much more advanced or specialized harnesses like Claude Code, where you have sub-agents and it makes a lot more decisions on its own about what it does next, including spinning up a sub-agent of some type. And so it really depends on what the goal of your evaluation is, whether you allow these things or not. And it also depends on the type of task that you have, whether this kind of thing may help or hurt performance. So as an example, let's say you're doing a big literature review and synthesis, and your goal is to come up with a new research idea, right? If that's your task. You could imagine that spinning up a bunch of sub-agents is very useful to do all of the paper reviews in parallel, but then presumably you still need one agent to synthesize everything and give you the final output. If you only had one agent doing everything, it might take a lot longer, or the model might get lost from reading one paper to the next. So I'll talk a bit about kind of these things a little bit later. And I'll give an example of a multi-agent setup that I think is interesting as well. Is that helpful?
Yep. So, thank you.
Cool. I think Richard.
Richard?
Yes, thank you very much. My question is going back to the scoring that you just introduced, and there was also on your slide the LLM as judge. So my question goes particularly in the direction of rating open-ended settings. Could you elaborate a bit on your experience? What is maybe common practice? Is it, for example, relevant to choose as an evaluator a model which is of a different policy, or does it not so much make an impact?
Right.
Can you generally recommend maybe some readings or something to look further into this topic on problem?
Right.
Thank you.
Yeah, so I think for it really depends on the type of agent eval. So I think I had this big list earlier. I think many of those agent evals don't use LLM as judge, but I think increasingly we are seeing them being used for. I think there's a bunch of benchmarks looking at kind of research and development. So can models reproduce papers? And then what people typically do for the judge is they have a structured rubric of the key criteria of what success looks like, which then gives the judge instructions for how to grade each one, what specific things to look for in the final solution of the agent. There's a huge literature on judges. There's lots of different biases that they can have. There's questions around how calibrated are they. Maybe one paper I would recommend from AC is 7 Steps for Transcript Analysis. I think a lot of the lessons there apply to judges as well. You basically, if you want to use LLM as a judge, you have to like look at the transcripts yourself. You have to look at the outputs yourself, develop the judge kind of iteratively, develop that rubric iteratively, and compare it to some ground truth answers. Look at if it's biased or not, look if it's calibrated to your judgment or not. And then sort of the paper outlines sort of a process for how to do that in a structured way that hopefully can give you a much higher quality judge. Whether it's, for example, it's biased towards its own generation or not, it really depends on the task. I think there isn't a hard and fast rule. You just have to check.
Perfect. Thank you.
Cool. Okay. So yeah, scaffolds. I don't want to go into too much detail about like all of the different types of scaffolds and things like that, because there's loads and loads and loads of them. Everybody is coming up with new multi-agent and sub-agent and different kinds of architectures. It does matter what you use, but it depends a lot on the type of task that you have, whether a particular scaffold is more or less helpful. There are cases where the scaffold can improve your results by more than 2x for the same model. There are cases where a scaffold that works with one model may actually hurt performance with another model. So it depends a lot on, there is like the sense of like this scaffold and model interaction. Is the scaffold helping the model or hindering it in some way? Is it making the task easier for the model? So for example, one aspect of scaffolds that I think is getting more attention recently is context management. So if you want to run a task for very many tokens, you might quickly hit the context limit, the context window limit of the model. Or if the task is complicated, that context window may get in some sense polluted with loads of stuff that the model is outputting over hundreds of turns, and maybe the model gets lost. So sometimes people call this context rot. There are other kinds of context failures. And so there's scaffolds that are much more structured in managing the information in that context, or removing it, summarizing it. And in some cases, this can help significantly. But there's many dimensions in which you can vary these scaffolds, not just around context management. I think just look around, look at what people are actually doing, and you'll sort of get a sense of the kinds of things that can vary. Okay, so this is a nice example that I like that maybe kind of goes into a bit more detail on some of these design choices. So there's a really interesting blog post from the Anthropic Engineering blog by Nicholas Carlini, where over about 2 weeks of time, he built a C compiler from scratch using 16 parallel Claude codes. He used 2 billion tokens, and it cost about $20,000 in API credits. And the output was a 100,000 line Rust compiler that passes a whole bunch of test cases. And you can read the blog post to get a sense of like what are all of the details that matter, how he iterated on this, all of the different complexities and failure modes. I think this is maybe a place I would recommend to start to get a sense of like where the frontier is on these things. And some of the lessons I like from this blog post are the test quality. So what kind of feedback or what kind of verification you have that the agent itself can use to make progress or to know when it's gone down the wrong track can be much more important than how sophisticated your scaffold is. So this is coming back to a point I made earlier about, can the model know if it's making progress or not? Can it verify its own outputs? Another is around context pollution, like I mentioned a second ago. He has some interesting comments there about designing the scaffold that makes it sort of easier for the agent to not get lost, to find the right information when it needs it. And this point about parallelism, I think I've alluded to again earlier. He had an example where these 16 agents were all trying to fix the same bug at the same time and overriding each other's work. And then he had to put in a system to prevent them from doing that. Right. So I think that's also interesting, is like just throwing parallel agents doesn't necessarily help. You have to do work around that to make it actually function. And this, of course, also depends on the properties or structure of the task. Is the task genuinely decomposable into units that you can do in parallel and then bring those results back together? Some tasks may not have that. Some tasks are maybe much more naturally serial. Yeah, I really recommend this blog. Okay, so another dimension that matters a lot that I think is still kind of undervalued, at least when people report results or scores, is inference scaling. So this is around how much budget do you give the agent to work on a particular task. Because you don't want it to run forever, people put in specific limits. If the model has not succeeded by a certain number of turns, like 100 or 1,000, or if it's used a certain number of tokens, like 100,000, a million, 100 million, then the task just ends. So this is kind of a part of the task environment that you have to set in place. Sometimes people use time limits, so a lot of wall clock time. Some people use multiple of these at once. There's a lot of variation in what people are doing, and I think it's important to, when you're reading results, to check for this as well. What was the actual limit? The reason this is important is that for some types of tasks, for some areas, some domains, performance can vary really, really significantly depending on how much budget you give the agent. So the plot here on the right is results from AC's cyber task. So this is about 100 capture the flag challenges across varying difficulty levels that are framed as capture the flag challenges. And the x-axis is the number of tokens that the agent was allowed on a log scale. So it goes from less than 10,000 to 50 million. And the y-axis is the success rate, the average success rate across these 100 tasks of a set of agents. And you can see that it's very linear, especially for the post-November models. So what we did here is we took a couple models that came out before November 2025, a couple after November, averaged over those, and looked at the success rates of these runs. And one thing to notice is how linear this line is, and the other is how it's increasing, how it's improving over time. And the linearity in particular is over many, many orders of magnitude. And before we noticed this effect, we used to run at about 2.5 million tokens maximum per task. And so you could see the effect that would have had. I think the success rates would be under 40% or so. And if you run to 50 million, it's maybe 65 or 70%. And very often people don't report enough what their token budget was, and maybe they don't even allow the agent a big enough budget to see its kind of true performance or how good it can get. There are other methods for implementing inference scaling. Here I'm just talking about letting it run for longer. There are other more complex techniques that sort of do versions of best of n, majority voting, other things like this, and those can also have an effect. In some cases, you can get diminishing returns. It's kind of a complicated area, what works and what doesn't. I think my point here is more, this can be a big effect. Be careful in like noting this in how you set your budget. If you set a budget and you observe one of these inference curves and the slope looks positive and very linear, probably you should be setting a bigger budget if you want the best performance. I think there are cases where it doesn't work very well. And my sort of hypothesis is that it works best when there's a kind of grounded local feedback. So this point about, can the agent self-verify and figure out if it's making progress or not? If that's the case for your task, probably inference scaling is going to work, unless the task is really, really, really hard and requires extreme domain expertise that maybe the models don't have yet. But maybe that's more rare. If the task doesn't have this kind of good local feedback, then maybe inference scaling isn't going to work, or you have to do something more clever rather than just running it for longer. Any questions on that? Cool. Okay, let's move on. So I've kind of talked about a bunch of different things that scores, benchmark scores, success rates, model performance depend on. So typically this is a function of which model you're using, which scaffold you're using, how much compute you give it. So the inference scaling question I just talked about. Obviously the task that you're giving it. Some tasks are much easier than others. Sort of going back to that decomposition of task dimensions that I mentioned. And of course, the kind of grading that you have. So I'm slightly belaboring this point, but I think it's important. So you can have the same model with different scaffolds can massively change your scores. Same model with more compute can change your scores. same task, and if you just fix grading errors, if you're just more careful with your grading, you can also increase your scores. And this is sort of more and more known in the literature of how sensitive these things are. So all of the sort of numbers I've given here are from some various papers and people sort of checking on these things. And so before trusting any result, when you're looking at a paper or a model card, sort of ask what was the protocol used, what were the settings, have they looked at their grading, have they done transcript analysis to check for issues or errors, is the model kind of hobbled in some way, maybe because it doesn't have enough inference compute for the task. That'll give you a much better sense of how much to trust the number. One other thing I want to talk about in terms of scoring is sometimes you'll see metrics reported in papers like pass at K or pass hat K, and they mean very different things, and they kind of tell you about different aspects of performance or capability. So pass at K means what is the frequency or the probability that you see at least one success in K attempts. So let's say you have a task and you run it K times. What is the probability that there's at least one success in those K? And there's a particular formula for calculating this. I won't give it here. This kind of tells you about the peak performance of the model. In some cases, what you care about is if the model succeeds once in 10 times, then I'm good, because then I just have to try it 10 times and I'll get the right answer. And so, for example, maybe your task is some kind of scientific discovery, right? You don't need strong reliability. You don't need it to succeed every time. If the task is a cybersecurity challenge, maybe you're measuring cyber offense skills of models, and the model is trying to break into some network. Again, maybe you don't need it to succeed every time. And so people report things like pass at K for these kinds of things. And then pass hat K is more about reliability. It's asking the question of how often does it succeed all K times for some number K in some number N of runs. So this is very much, can you rely on it to be sort of robust? Pass at K typically goes up with K. So if you have the probability of succeeding once in every 2 attempts will be lower than the probability of succeeding once in every 10 attempts. It's a kind of exponential. And then pass hat K tends to go down with K because the requirement is getting stricter. So if pass at 1, so the pass at 1 is like the average success rate, then pass at 5 might be 97% if pass at 1 is 50%. So, and pass hat 5 might be 3%. When you read papers, you'll see various other kind of metrics that people use. I think these are sort of the core ones that others are based on. And the thing to remember here is, are you measuring some notion of like rare peak performance? Are you measuring reliability? Or are you just measuring the average? And any questions on that? Good. Okay, let's move on. So next I'll talk a bit about the validity of your measurements. Like, what are your scores actually telling you? And what kinds of things affect this? So maybe we can do a quick exercise on this. Imagine you're evaluating a coding agent on a new benchmark you've never seen before. And maybe you just need some results really quickly, and you haven't read the paper carefully, you haven't looked through the tasks, and you get 40% score. And maybe you care about the score. You either have to report it in your paper, or you have to go to your, research lead or line manager or whatever. And the question is whether this 40% is good or bad number. Before you report this number, what questions should you be asking? What could have gone wrong in your agent eval? I think it'd be interesting for people to sort of think about this for a couple of minutes, and then we can discuss. I'm curious what kinds of things people maybe have observed, or what kinds of things do you think can go wrong that I haven't talked about? So think about it for a minute or two, and then put up your hand and give me some examples. Okay, should we start? Does anybody have any any good questions you should be asking about this number? What could have gone wrong? In the chat, is the performance in the ballpark of your expectations? Yeah. So this is kind of talking about, do you have something like a baseline or a prior on what performance could look like? Maybe you're trying to reproduce a result from a paper you've seen. So the question is it even close to what they get in their paper versus what you've gotten? And then, is the performance robust under environmental changes that should impact the score? I wonder, could you give some examples of what such environmental changes are, Richard?
Yes, sure. I mean, my first question was, for example, I mean, let's think of data contamination. Maybe there is a
Right.
certain information that leaked into the training data,
Yeah.
and maybe I can say, can I, for example, take an older training point of the same model where I know, okay, the evaluation, the paper was maybe released after this, so it couldn't be in the training data. So
Yeah.
if the performance is also the same there, I can maybe say, okay, it could not have been due to data leakage.
Yeah, that's a really good example. In fact, OpenAI had a blog post recently where they are deprecating SweBench verified. So this is one benchmark that has been used by OpenAI for a long time in their model cards, and they're no longer using it exactly because of concerns about contamination. That there are many solutions to these tasks everywhere on the internet that are possibly now in the training data of their latest models, like GPT 5.4 or whatever it might be. So they're deprecating it. Another environmental factor I haven't talked about that I think is kind of fun is if your agent has web access, has it just looked up the solution? So it doesn't have to be in the training data, but maybe there is a solution online. And so it just goes and looks it up and you haven't noticed that. And so in some sense, you're overestimating the agent's true capability because it can just go look it up. Unless your task is to test whether it can go look up answers on the web. So it depends what your task is as well, whether that's an environmental factor that pollutes your score or not. Depends on your goal for the task. Anyone else?
We have Jody.
Mm-hmm.
And
Yeah,
Julie.
my first thought is about the actual benchmark, right? So you have 40%. What are the items? Which items contributed to the 40%? Which are the ones that you didn't get, that didn't do well with?
Yeah.
And then, of course, the settings, which we've been talking about.
Yeah. It may be that, let's say you run 20 different models on all of your items, on all of your tasks in your benchmark, and you notice that there's always one task that no model ever gets. Maybe it's worth looking at whether there's something wrong with the grading or the task is somehow impossible because of the way it's set up, right? Yeah. The score doesn't tell us anything about the eval protocol, level of difficulty, how many items, current benchmarks, best practices, etc. Yeah, that's right. So I think one thing in terms of scores is kind of combining these 2 points from Jody and Julie is it's worth looking at the individual items. What were their scores? What were their averages? Or separating out your tasks by some notion of difficulty or topic or something like that, rather than just reporting the average.
And then we have some more comments from Laurentio. Is the measurement within or outside the boundary of known capabilities of the model?
Yeah. So for example, let's say that you know the history of success rates of other models on these tasks, and no model has ever reached above 3% before. And suddenly you have a model that's reached 40%. Is that because it's cheated somehow? Is this actually a true capability jump? Which of course can also happen. We've seen big jumps in the past. But there's this question of how big a jump is it? Is it plausible? And then sort of going in and looking at whether it's real or not.
And then we have Harmonia say, I think the best benchmark should make the grades following some distributions.
Mm-hmm. Yeah, I think that's a good idea. It can be tough to ensure that that's the case over time. So you can, and of course, do this at any given time for any given model, but you may not be able to do this for models starting from today, from 6 months from now. If models are improving in their capability, your scores will tend to compress on the high end, right? So then you need to add new tasks or make them harder, You need to edit your benchmark. If your goal is to discriminate between models, to have a really accurate estimate of which model is better, then it is really valuable to have this kind of distribution.
And then we have another comment from Daniel. Similar to what has been mentioned already, it's important to know what the model actually did. Regarding the task design, did we account for shortcuts, unintended methods that trivialize the task? Is the agent cheating in some way we didn't think about?
Yeah. I think that's a great point. I'll talk a bit more about transcript analysis in a couple of slides, which is exactly focused on this point. And then let's do one more. So what kind of problems did it fail on? Syntax errors, logical reasoning, edge cases, or failure systematic or random? Yeah, I think this is also something that's worthwhile doing if you want to get really deep into understanding your scores. And transcript analysis can be helpful with this as well. So we'll cover that in a second. Okay. If people think of anything else throughout the next few slides, throw them in the chat. We can talk about them later. Yeah, thank you, everyone. Okay, let's move on. So this is a kind of hopefully intuitive, structured way to think about validity of your results. So first you have your scores. And from those scores, you want to make some kind of an inference about the capability of the model. And that inference has a capability or safety of the model. And that inference has a few steps or like links in this chain that I think a bunch of the examples kind of alluded to. So the first is people call internal validity. Does the score reflect real capability of the model? And so there's a couple of ways in which that may not be valid. So one is overestimation, right? So the agent can find answers online rather than solving the task itself. As I mentioned, SweBench may have this issue. There's also, I think, been examples where the agent was able to access future Git commits from the logs of the repo, of the GitHub repo, and in some sense cheated because of this. And so therefore the score doesn't reflect real capability. There are also examples in the literature where agents have modified the evaluation code to report success when in fact the success was fake. There's also, of course, underestimation risks. Maybe the model refuses to engage with the task if it perceives it as dangerous in some way. So maybe it's a capture the flag challenge or something that violates the policy of the model. And those refusals may be hard or they may be soft or the model may just be disengaged in some way. And you may get low scores not because of a lack of capability, but because of refusal or disengagement. Of course, there's things like tool call errors. If your environment is not set up properly, then the tool calls will fail and your score will be low. And we've also talked a little bit before about grading bugs, right? Is your grading actually measuring what you think you're measuring? On this point about models cheating, so sometimes people call this reward hacking, and there's different flavors of this. And I think there's some results that the possibility of reward hacking is scale with model capability. So the more capable models are in general, the more able they are to reward hack or find alternative solutions, sort of clever ways around the intended path of the task, the intended solution of the task, that things that make the task easier to the model in some way. So I've given a few examples of these, but there's many others in the literature. And the concern is that as agents get more capable generally, they're just better at finding exploits. And I think this is kind of an open question, especially around how to deal with this kind of problem. And so as models get better, your evaluation needs to be more robust to this kind of cheating. And it can be very hard to do that because the task environments are also getting more complex in terms of the software complexity that's required to set everything up and to run it. So there are a couple of really good papers I recommend people look at. One of my favorites is Best Practices for Rigorous Agentic Benchmarks by Daniel Kang and a bunch of other people. So they did a really rigorous deep dive on dozens of benchmarks looking for all kinds of issues, and then developed a kind of checklist, the ABC checklist. that can help you review benchmarks, can help if you're developing a benchmark, can help you sort of check for different kinds of issues to make sure it's that what you get out is high quality. I won't go through all of these, but they're roughly the kinds of things we've talked about, like verifying the sort of ground truth correctness, isolating the agent from the solution, making sure that each run is independent, etc., checking for solvability, right? Is the task actually solvable? But there's a bunch of others as well that are worth looking at. Yes, thank you for posting the paper in the chat. And so I think this paper is really nice for these two reasons. One is you get a sense of all of the kind of failures that have been observed, and also you get a checklist if you're developing evals or running evals. That can be very, very useful. Yeah, any questions on that?
Oh, yes. These evals essentially are kind of in-lab evals, right? That I mean, I tried to make an eval in lab to measure some specific capabilities, but are there evals out of the lab once deployed, for example? Yeah.
So what do you mean by out of the lab?
Like, say, for example, I am in the healthcare industry and I want to, I am setting, I don't know, several agents that would control, I don't know, invoices. Yeah, I need to know if they are kind of useful or they're just invoicing well to the users and so on and so forth.
Yeah.
Have been any like projects in that sense, like just when you bring systems on the wild?
Yeah, my guess is yes, there's loads and loads of these things across everything you can imagine. Probably many organizations also have internal private evals that they don't share publicly for various reasons, maybe because they're very tied into their internal infrastructure, information security concerns, privacy concerns. And maybe they also don't want their evaluations to be gamed or to end up in the training data. But I think generally, as organizations develop agents for internal use cases, you need evals, right? You need to measure some aspect of the capability, the performance you really care about, and then you probably have to develop your own. Cool. Okay, let's move on. A tiny bit more on this question around graders and outcome validity and failure modes around this. So we've talked about different types of graders earlier. So code-based, model-based, and human. So code-based graders are fast, of course, and reproducible, but can be too narrow. So narrow in the sense of rejecting correct solutions. Or they can be too wide in the sense that they check for things that are not specified in the task. So for example, in the OpenAI review of SweetBench Verified, they noticed that a bunch of the tasks had testing issues. So more than a third, I think, had tests that were too narrow. So they rejected correct solutions, which means that the scores that were reported were too low, right? So the model did in fact solve the task, but the tests failed and said that the task was not solved. And this happened for SweetBench Verified. Model-based graders, so LLM as judge that we've talked about a little bit about, are of course more flexible, but you need calibration. They can be non-deterministic. You need to run them a bunch of times, ideally. They can be biased for different things, which the bias depends a lot on what your task is, what models you're using, whether there exists a bias or not. And then, of course, human grading. The issues with human grading are that they're expensive, they're slow, they don't scale. If you have 100 tasks and you're running each one 20 times, you don't want someone to be staring at hundreds of pages of transcripts all day long. But in some cases, they're very valuable. So some people do this. I think GDP Val has expert human graders, if you're familiar with the GDP Val. And generally, I think depending on how important your results are, how sort of what is your use case, how high stakes is it, you probably want a mix of all of these, and you want to have a really sort of good verification loop and calibration and checking for bias. So I think I mentioned this paper before on transcript analysis and judge development. That has a good sort of breakdown of like the 7 steps that you should follow, especially if you're doing LLM as a judge. And I think it's referenced in my last slide if people are interested in it. So I've alluded to transcript analysis a bunch. Let's talk about it in more detail. So like people have noticed, and like I've mentioned, scores alone can't distinguish between the model lacking capability, the setup being flawed, or the capability being poorly elicited because of a bad scaffold or a bad prompt or something like that. And so one increasingly common technique for getting much more insight and information into these things is transcript analysis, but it has its own trade-offs, it has its own issues. And so this paper I mentioned, 7 steps for log analysis, goes into how you can hopefully do a sort of systematic, good job of developing transcript analysis tools, graders. And I would say it's one of these things where it's getting the basics right. It's nothing fancy. It's just do the obvious things, do them well. It takes time and sort of attention, but it's worth doing, especially if it's something high stakes that whether you're building an eval or running an eval. Yes, Jody?
I just want to clarify that when you say transcript analysis, are you talking about like error traces, like of what the agent's doing, or is it something
Yeah,
like
so
what
I
is
would say,
it
yeah, so by trace, do you mean code trace or more general?
Yeah, basically like every step the agent's taking, there's like a log, like log data.
Yes, the
That
logs, yes. So by,
okay.
by transcript, I mean log, yeah. So
Okay,
it
got it.
doesn't have to be just the errors. It can be the behaviors of the agent, its
Like tool
reasoning,
usage.
the tool usage, how
Okay.
it's making decisions on what it does next. Um, of course, you can focus on the errors, like tool call errors, and you can build transcript analysis tools just for detecting those errors. But you can also look at more general behaviors, like let's say you're comparing 2 scaffolds in terms of how the model is making decisions about what to do next. You could potentially use it for that.
Okay.
You can use it for quality assurance for your eval design, right? Though, is the environment working properly that the agent is in, and checking for whether the task is even solvable. So for example, let's say your task is a capture the flag challenge where the model has to get into some network. Well, is your network actually accessible?
Okay.
Otherwise, the agent will just fail every time, right?
Yeah.
And that doesn't reflect capability. So yeah, basically anything where you actually look at the logs, you can build transcript analysis tools around. And depending on how complex your behavior or the thing you want to check for is, this may be more or less easy, of course, right? So if you're looking for things like strategic reasoning, or is the agent, I don't know, sabotaging your task in some way, maybe that's much harder to capture
hmm
than something like a particular tool call error that you want to fix. Maybe that's
Okay.
easier, sure, right?
Got it. Thank you.
Okay. The 7 steps are written here. Basically, what you would normally do in like a sort of research project: define your question, figure out exactly what data you have a good ground truth, have a coding scheme for what you're actually measuring. So what is your grader looking for? How are you encoding that in the rubric? What are you asking the judge to output? And in terms of validating your results, I think it's really important to do this kind of development set, test set split, where you're developing your grader on one set of transcripts and iterating on it, and then at the end you test it on a second set of transcripts that you haven't seen before, so you're not overfitted to those transcripts. There's a nice taxonomy of types of failures from Meter that I like. I think it's under their elicitation protocol webpage, where they talk about spurious bottlenecks, which are kind of fixable issues, real bottlenecks, which may reflect capabilities, or things that may lead to trade-offs. If you want to sort of dive deeper into these kinds of topics of the kind of issues you can see in the logs or in the transcripts. So in terms of getting the best results on in your agent evals, I think the AC published an elicitation protocol a couple of months ago, as well as Meter has one that I just mentioned. And sort of my suggestion, or the approach that is outlined in these blog posts, is to do this kind of iteratively or progressively. And so look for egregious failures first and try to fix those first. Is the model refusing? Is the output in the wrong format? Are the tools broken? And just trying to fix all of these things that are kind of just like basic quality assurance. Like, is the thing actually doing what you want it to do? Then you have to verify scoring. So the formatting or other kinds of issues that I mentioned. If you don't verify scoring, you don't know if it's 40% means an overestimate or underestimate. You don't know if 0 means the model is not capable or something's broken. Then, of course, there's tool use. Sometimes I think people try to give agents many tools, and that can actually hurt performance because the model can get confused or lost in what tool it's using and how to use it. So there is this question of like, is it the right tool? Is there a right number of tools? Is the tool necessary? And in terms of improving the prompting for the task, sometimes people set up tasks where they give the model some kind of structure or hints or output formatting suggestions or things like that. There's often simple things you can do to improve performance that aren't kind of leaking what the task is about. And then I think only after all of this, you should try maybe more advanced techniques like fancy scaffolds, multi-agent scaffolds, things like that. Yeah. Any questions on that? Cool. Okay. So the last couple of slides, I try to sort of put everything together and talk a bit about what I think are interesting directions that agent evals are going to go in the future. First, system cards. So if you look at system cards, they often have many sections that talk about agent benchmarks. And I think these are increasingly reported better and better, but there's still issues. So typically you'll see many benchmarks across many domains like coding, web development, web access, web search, cyber, research tasks. People typically report different levels of inference compute or reasoning effort. And there's often external evaluators involved that have their own private task sets like Meter, UKAC, Apollo, and others. And sometimes you'll also see contamination analysis, which is really great. So like I mentioned, the SweBench data leakage issue. I think OpenAI did this for GPT-5 and noticed this issue, and they deprecated SweBench. Now they're using SweBench Pro. What's harder to see or is often not reported in model cards are full scaffold details or the full specification that would allow you to replicate the results. Sometimes you don't see the compute budgets sufficiently, to my point before about inference scaling. And one other thing that is potentially an issue that's cropping up more and more is that models are often involved in the eval process itself. So if you're evaluating Opus 4.6, you might use Opus 4.6 as a judge, or for transcript analysis. And so there is kind of a question here. There's risks around doing this, of course, beyond bias, beyond scoring bias. So agent evals, where are they going? Meter have this time horizon graph that has become kind of foundational to people's thinking about agent capabilities. And in case people aren't familiar with it, it's a set of tasks which are broadly software engineering, research engineering, and each of them has been kind of designed to vary across difficulty. And by difficulty, I mean the amount of time a proficient human would take to complete the task. And they have tasks that would take humans 1 minute or 1 hour or 10 hours, I think up to about 30 hours now. And they've run all these tasks on models over the last 4 or 5 years. And if you do a bit of statistical analysis on these results, what you get is that the time horizon of models, so this is the set of tasks at which models succeed at least 50% of the time on. How long are those tasks if they were to be done by humans? That time horizon is doubling maybe every 7 months and maybe every less than 4 months more recently. So there's some evidence that there's been a trend change in the time horizon, maybe around the middle of 2024. And plausibly, the doubling time is less than 4 months now. And very recent models like Claude Opus 4.6 had around 12-hour time horizon. So if you project out to the end of this year, you might expect that the agent time horizons would be above 30 or even 40 hours. And the question then becomes, how could you even measure this? Because how can you distinguish between two models that have time horizons over 40 hours? Because then you'll need tasks that span up to maybe 80 hours. And this sort of measurement gets harder and harder as time goes on, if this trend continues. Because a few months after models hit 40 hours, they'll hit 80 hours, and then you need to build 80-hour tasks. A few months after that, you need 160 hours. And it maybe even becomes exponentially hard to build these tasks, or it becomes impossible. The reason I mention this is because this horizon plot and this notion, this measurement of capability, this metric, has become very foundational in how people are tracking capabilities and in the sort of safety and security world. And plausibly, we're going to lose the ability to observe this by the end of the year. And there's a big question of how we maintain that observability. What do we actually do about this problem? I think it's a really interesting question. Do we keep trying to measure this quantity? If so, how? What else should we measure instead if we're not measuring this? This is very much related to benchmark saturation. So loads of benchmarks that have been developed over the last few months are very quickly becoming saturated. So SciBench is one, CoreBench is another. I mentioned earlier that just using Claude Code, I think on Opus 4.5, doubled the performance, more than doubled performance, and now CoreBench is basically saturated. And loads of other sets of tasks are becoming saturated recently. And the question is, are people going to keep building benchmarks? If not, how do we keep track of capabilities? How can we distinguish between models as they're becoming more and more capable? Yes, let's move on. I think plausibly one way that this will go over the next few months at least is kind of an extension of the C compiler project that I mentioned earlier from Anthropic and Nicholas Carlini. So if you think about what that C compiler project was, it was kind of a multi-agent real-world project, or like large scope of work that plausibly takes humans many days or many months even. And instead of it being a binary pass-fail success criterion, there was a much more sort of complicated notion of what quality of success looks like. You know, in terms of the code quality, does it pass all these tests? How efficient is it, etc. And the other interesting thing about that work is it's very high cost and small n. So typically benchmarks have many, many tasks, potentially hundreds, and you run each one maybe 10 times. But because of the length of time it takes you to run it and the number of tokens you need to see success, you just can't do that anymore. And the question is, what do we do about that? Plausibly, one way to deal with this is to measure something like a performance surface across different configurations or variants of a task, rather than developing many, many different tasks. This is very speculative. I'm not sure if this is the right way to think about this. But this is plausibly one way things could go, is people will develop fewer tasks. They'll be much, much harder. They'll be like programs of work, real world projects, and they will run them much fewer times, many less samples than is typically run today. And this has all kinds of methodology issues in terms of what you can conclude about model capabilities, external validity, etc. And I'd be curious to see if people have thoughts on, like, are there alternatives to this if we want to continue to measure capabilities and understanding the differences between models a year from now. Any thoughts on that from anyone? Okay, I think it's a hard problem. It's an interesting one. The final thing I want to mention here is around inference scaling. So the plot on the right here is from a recent AC paper on a benchmark called breakout eval, which is a model is put in a Docker container, and its goal is to break out of that Docker container. In fact, it's placed in 2 Docker containers, so it's still contained. That's not escaping on the internet or anything like that. Its goal is to break out of the first one, and we can sort of measure how effectively it does that. And the set of tasks is split among a bunch of easy variants and hard variants. So these are the left and right panels. And you can the x-axis again for these plots are tokens, log tokens, or cost, also on a log scale. And you can see the general trend of from older models to newer models, how the inference curves move up and to the left and become more log linear for the easy tasks, and the beginning of this trend for the hard tasks. So you can sort of see that for recent models like GPT 5.2, the performance, the inference curve today looks maybe a little bit like, on the hard tasks, it looks a little bit like it did for a bunch of older models on the easy tasks. And an interesting question is, how quickly will it take for models to go from these sort of fairly quickly saturating inference lines to what it looks like on the left panel, where they're effectively log linear. The, I think, interesting aspect here is that I've alluded to earlier is what drives this inference scaling. What is changing? What is improving over time? What aspect of a task determines whether you get something that saturates quickly or is sort of this log linear shape? And I think there's kind of 5 dimensions here. One is verification quality that we've talked about. Can the agent tell that it's on track? Another is, can it self-correct? So not only does it know whether it's wrong, but can actually do something about it. Does it know what the right next thing to do is, even if it knows what it just did was wrong? Another is information management, which I think is increasingly important. As tasks are getting larger and longer and more complex, plausibly you just need more tokens to make progress. So for example, the x-axis on this plot, the scale here, is at about 10 million tokens. So the budget used here was 10 million total tokens before the task ends. In the previous plot I had on cyber inference scaling, it was 50 million. I think very quickly, to get signal on model performance on the hardest task, we may need to go past 100 million or 200 million tokens. And so the question is, how does the model manage all that information? Do you need something like context summarization or other more complex scaffolds? Another thing that I think is important for inference scaling, whether we observe it or not, is the search strategy. Is the model exploring effectively or efficiently? Does it commit to one sort of approach or strategy very quickly and then can't find its way back to try a different approach? Does it work sort of very iteratively, checking its work at every step? So I think this is an interesting aspect of model capability that is, I think, plausibly underexplored. I think is really interesting. And then the last one that we talked about earlier a little bit is parallelism. Is the task in some sense naturally decomposable, and you can take advantage of multi-agent or sub-agent systems, where you might see this kind of inference scaling much more be much more effective, or the shape of the curve is much steeper with extra tokens or extra sub-agents. Some tasks may not be decomposable easily, in which case maybe we wouldn't expect to see this kind of inference scaling. The reason I talk about inference scaling so much is that if you're interested in measuring sort of maximal capability or peak performance, if you don't run it for long enough, if you don't think about inference scaling, you're likely to underestimate. If you care about sort of safety or security of the models, if you care about things like capability thresholds, or for example, like responsible scaling policies that have thresholds on model capabilities in terms of what new safeguards do you need or new governance processes you might need, and you're not measuring this inference curve, you might get a false negative. You think that your model is below some threshold of capability or risk, when in fact it is above it if you were just to run it for 10 times more tokens for a larger inference budget. And I think this is currently undervalued in terms of how people estimate performance and how people report performance. Okay, so I think we're almost at the end. I think 3 main takeaways from today. Scores are functions of many, many details and choices, and it's important to track all of these to understand what people are doing, to know whether to believe a score, whether it's an underestimate or overestimate. Of course, it depends on the model and the scaffold, depends on inference compute, the task, the grading, etc. Changing any one of these can massively affect your results, can more than double them in some cases. And you should ask for transparency around all of these. And if you are writing papers, if you're writing model cards, if you're running your own evals and reporting them, you should be transparent on all of these because they're all very important. Validity requires sort of active work, active effort, checking lots of little details on all of the kinds of things that might lead to over underestimation. I definitely recommend reading the ABC paper. If you're thinking about developing new sets of tasks, use the checklist. It's very useful. Maybe there's things missing in the checklist as well that you should be thinking about depending on what you're developing. And in particular, transcript analysis can be or log analysis can be very useful for revealing things that are broken, for understanding how models are behaving. And if you're doing elicitation, I recommend doing this in a kind of progressive way. Do the simple stuff first, get the basics right. Before you go to super fancy scaffolds and things like that, just do the transcript analysis, check your graders, check your tool errors, etc. Otherwise, you might get lost in all of the details of the more complex systems, which have larger surface area for things going wrong. And finally, I think agent evals are changing very quickly. Time horizons are plausibly doubling every 3 or 4 months. Potentially, they'll be at 40 plus hours by the end of this year, which means we're going to run into something like a measurement problem. Benchmarks are going to saturate very quickly over the next year. They already are. And our evaluations have to evolve, and it's unclear how they will evolve. One plausible approach is this Carlini C compiler style, very hard, large program of work. But that may not be the right choice. That may not be the right direction. There may be others people will come up with. I think this is a really, really interesting research question. In particular, if we do go in this direction of these large challenge problems, how do we actually get signal out of them beyond the final score? If we have hundreds of millions of tokens, how do we get the most insight out of that? And final point here is capability is not reliability. I think looking at reliability is currently undervalued. I think there's some really interesting recent papers looking more at reliability. But I think there's a lot of interesting open research questions around reliability beyond sort of the average score. And here's a couple of recommended readings that I mentioned throughout the slides. I'll share the slides after this with the course if people want to note these down and have a look at them. Any questions?
Yes, seems like we have a couple of questions that are just arriving here on the chat. I can read them, but do you want to ask them yourself, Laurentio, Rodrigo?
Yeah, sure. I can ask my question. So, do you see the evals moving more towards a place where we have evaluator agents per se that can adjust dynamically, not only assessing a fixed set of capabilities, but trying to push the model that's being evaluated more to see where it can break, avoiding a match where there's a reward hacking or there's an overfitting or anything on that?
Yeah, I think plausibly that's another interesting direction. There's been more work on this recently around things like alignment red teaming. So there's a tool called P-tree where you get one model to act as the environment for a target model, testing for things like sabotage or other aspects of alignment. The question there is how can you how can you make sure that the environment is realistic enough for the target model, and that the model that is doing the evaluating, the auditor, is behaving sort of on policy, is behaving according to what you wanted, how you want it to behave, that it's giving the right environment feedback. So there's a lot of challenges around getting models to be the evaluators. But plausibly, these techniques are going to improve over time, and it's going to become more important rather than having like static evals as they are today.
Thank you.
Thank you, Lorenzo. Okay, Rodrigo, do you want to ask your question or you want me to read it?
I'll try. Thank you. So thank you pretty much for the lecture. It's a pleasure for me. So are there any indicators related to the agents' capabilities, efforts associated to the outcomes? I mean, for example, do you know if it's possible to assess the agent's reasoning process, more qualitativities, things like something like this, and then judge the performance together?
Yeah, I think this kind of thing is interesting. I'm not aware of any really good papers on this. But I think, for example, yeah, you could look at the chain of thought using transcript analysis tools. I think the challenge there will be like exactly what good looks like. What is a good reasoning process versus a bad reasoning process? What aspect of the reasoning are you interested in measuring? And trying to encode that into a rubric that accurately captures that. If it's something that is very, very qualitative, that requires kind of a lot of human insight or taste in detecting whether it's there or not, that might be very hard. But I definitely think it's worth exploring this kind of things. Another technique may be to run an agent on a task, observe its reasoning process, and then go in and edit it. So sometimes people use these kind of techniques. So you take the chain of thought at some step, like turn 75, and you change it. You turn it from good to bad or from bad to good. And then you run the task from that point forward, and you see how the behavior changes. So this gives you more of like a causal analysis, right? You're directly intervening in the output of the model and then running it from that point forward again. And so you get to observe both conditions. I think stuff like that is very interesting as well.
Thank you, Rodrigo. We have a question from Julie. Julie, you want to ask it?
Yeah. Hi, Cozmin. That was really, really interesting. You know, we haven't really dug into it, but we've talked a little bit about propensity to act, right? In addition to capability. And I'm wondering, and I'm interested in propensity. If we move towards the larger, fewer evaluations, I'm wondering if you have any thoughts about how to wedge in propensity to those sorts of evaluations.
Mm-hmm. Yeah, I think to me the question here is propensity for whatever propensity you're interested in, right? For sabotage, misalignment, etc. Is our propensities affected by how long the agent is running for? So you might imagine if you're measuring propensities in a sweep bench type task or whatever, like 10 turns, right? Let's say that's as long as the task is. Whatever propensities you might observe there versus 100 turns versus 1,000 turns, 10,000 turns. Or propensities with multi-agent systems and how the agents are interacting with each other. If you think propensity plausibly is affected by that, by the scale, then you have to measure it, right? There's no way around it. Or at least you have to make some argument why propensity doesn't change from 10 to 1,000 turns. I think plausibly it's an interesting research area. Can models kind of diverge from their assistant personas or change their propensities massively after 1,000 turns because of some kind of chaotic effects or the model sort of compounding on itself based on its past outputs?
So then it sounds like there may be behaviors that we'd only observe if we move to this larger,
I
more
think
complex.
so.
Yeah,
I think that's a really interesting thing to look at. I don't know if anyone has. Like, do we see massively different or new behaviors after 1,000 turns versus after 10 turns? Yeah.
Interesting. Thanks.
Thank you, Julie. Any more questions or comments? All right, well then, a round of applause for Cozmin. Thank you so much for coming and joining, for making time in your busy schedule at the AI Security Institute to come teach us and share, all the most relevant and current research on the topic. Thank you everyone for showing up and for engaging as you did. It's been lovely to have you once again, to all the familiar names that we already are getting to know here in the community. Tomorrow we have another open seminar. It's going to be a little bit earlier. You can check the details in our website. I shared the link in the chat. And please, please, please rate this session and let us know what you think, if you liked it, so then we can say to Cozmin, they loved it. Fantastic, and we can give like really great feedback to him. Thank you so much for being here, and we'll see you next time.
Thanks, everyone. Have a good day.
Bye.
Bye.